What is going on, everybody? It's Mr. Gus. I'm in the physics conference room with a bunch of my circuits and resistors materials. Today we're talking about real batteries versus ideal batteries. I've got an example of both here. So far this unit we've discussed a lot about ideal batteries. And ideal batteries are what we plug into the wall. It's this guy here. It's our battery eliminator. It's our power supply, right? This guy is considered an ideal battery. What that means is that whatever my voltage is rated at is exactly what comes out of the battery. Let me show you. On here I've got a dial. That dial tells me 1.53, 4.5, 6, 9 volts. If I go ahead and I take my multimeter and I plug my multimeter, in this case I have it turned on to a voltmeter, but if I plug this thing in to the battery and I turn it on and it's on at 6 volts, well, guess what my multimeter reads? It reads basically exactly 6 volts. There's a little bit of not, but maybe that's an old battery, who knows. But it's gonna always read this, no matter what. If I add something to it, if I go ahead and I say, let's put a light bulb, a Christmas light or a little holiday light, a little decorative light. If I light that sucker up, here it is. There's a load on it. Now there's a resistor attached to it. Look what happens to my voltage. There's no change, right? A real or an ideal battery is going to maintain its voltage no matter what. That's what it does, okay? There's no resistance to it. There's no loss of voltage to it. It maintains this regardless of the load I put on it. Now, a real battery is something like you and I might pick up at the store, go to Walmart, go to Target, wherever your shopping is, and we would find an ideal battery, or a real battery. These real batteries are made up of chemical reactions. It's different than the ones you plug into the wall. The ones you plug into the wall have a converter in them, and they transform the voltage at the wall, and then they output that voltage through into the wires. This, though, is made up of a chemical reaction. It's a redox reaction. If you're a chemistry nerd like me, you understand the chemical reaction. But basically what happens is the reaction takes place inside the battery. Let's go ahead, without this battery plugged in, we say without a load on the battery here, let's go ahead and check and see what its voltage is. I can go ahead and just pop that sucker in here. It says on the battery, these camping batteries, these big like lantern batteries are rated at 6 volts. So I've got this thing plugged in. Let's see what it says. When I've got it plugged in, there's no load. It's just I'm just testing this thing for its voltage. It's bouncing around right now for some reason. That's weird to me. But usually it sits at about 6 volts. It's dropping dramatically. Is this getting warm? There we go. Maybe it's just a bad connection. There we go. Under a good connection, it sits at 6 volts. I don't know why it's changing so much right now. It wasn't before, but it should sit at 6 volts. Let's just get a really good connection here between these leads. There we go. There we go. Now we're rock solid, right there at 6. Okay? So without a load, the battery actually does test a little above 6 volts, which is interesting. Let's watch this now. What if I go ahead and instead I'm going to leave these attached here, connected to the battery, but now I'm going to go ahead and use the battery like we should. And when I use the battery like we should, and I go ahead and I, get that in there on one side, touch this to the other lead, I turn on my light bulb. So now the battery is powering this light bulb over here. It's plugged in. Let's see what that did to my voltage. The voltage is now reading 5.5. It's reading a smaller value, okay? This is because the chemical reaction takes place inside the battery in order to maintain its voltage. Now, the chemical reaction inside there isn't perfect. It has its own issues and its own inefficiencies based on the way the battery's built. So in order to do that, it's only able to maintain a voltage of 5.5. That chemical reaction is only able to maintain a potential difference of 5.5 or so. Watch this though. If I go ahead now and I add a second battery, or a second light bulb in series to this, let's just go ahead and clip these together and see what happens. If I add this, I'm going to add it in parallel. I said series, I meant in parallel because I'm just going to attach them to the same leads here. But now I've got both Christmas lights are both on, and my voltage is dropping even a little bit more. So the more load that I put on this battery, the more that chemical reaction needs to keep up, right? It needs to supply 5 volts to both of those light bulbs because they're in parallel. In order to do that, that reaction has to really work. And so as it works and works and works, it can't maintain 6 volts of difference in the reaction. So instead, we get the reading of a little less, 5.5 or 5.4. It's maintaining that. Here's the difference, okay? Let's take a quick note on what the difference is. If I can find my marker. Where did my marker go? Where did it go? Where did it go? Where did it go? It doesn't matter for now. For now, an ideal battery. An ideal battery, oftentimes, the voltage is called the electromotive force, or EMF, because we know that no matter what, this voltage is going to be 6 volts the entire time, or whatever the battery is rated at. There is no loss of voltage or loss of energy or inefficiencies in an ideal battery. And we would model it like this. Sometimes we got 3 cells, sometimes 2 cells, doesn't matter. Over here with the real battery, a real battery is slightly different. A real battery is essentially, it's always measured in potential difference or voltage, not EMF, because it's not ideal and it will change. What it's measured in though, or how we draw it, is we draw it using the battery symbol as before, but there's also, it's hard to see, a little resistor drawn here. There's a resistor in series with that battery because the battery acts as though there's internal resistance. And so we call this right here the internal resistance of the battery. Okay? Resistance. So when we're talking about ideal versus real batteries, what we're actually talking about is there an internal resistance on the battery? This is the concept. Let's go ahead though, now that we know the concept, let's go see it in practice. What's a question I could ask you about internal resistance? So we'll do this over here. I got a problem on the side of the board. You can take a minute, jot it down if you want, but here I've got I've got a parallel circuit. I've got a real battery rated at 12 volts. I've got an ammeter, or a current meter, plugged in. It reads 2 amps. So the total current leaving this battery is 2 amps. The battery is rated at 12 volts. That's what's printed on the battery. It enters this parallel circuit. I see 2 loops. I see a 10 ohm loop and a 5 ohm loop. My question to you is, what is the internal resistance of the battery? Let's break this down together. In order to find the internal resistance of the battery, what I need to figure out is, at 12 volts, is 2 amps the max current that should be going to these 2. If this is smaller than what Ohm's law would tell us it should be after I know equivalent resistance, well, that means there must be some resistance in the battery. So let's check this out. Let's go ahead and find the total resistance of this. If I find the total resistance of this whole branch, I would take 1/5 ohms plus 1/10 ohms, and that's going to be 1 over the equivalent resistance for a parallel circuit. And so I add those together, I end up with like 3/10 equals 1 over R. I end up with Req. The total resistance for those 2 branches ends up being 3.3 repeating ohms. This is my total resistance for both of those. So now I've got total potential difference, total current, and total resistance. Let's go do an Ohm's law equation for all of that. I've got V total should be equal to I total times Req. Let's plug these in. I get 12 volts here is equal to, I want to find out if 12 volts matches that. I want to go ahead and say 2 amps, which is total current, I measured that, times 3.3 ohms, I know that, should be equal to V total. When I do this, I end up with the V total, like what potential difference causes that current at that resistance. I end up with 6.67. We'll call it that because we know that it was a repeating number. So I end up with 6.67 volts, which is weird because I know that, did I use 12 volts? I did use 12 volts. Because I know that I should be having 12. Like the battery should be supplying 12 volts and it's only supplying 6.67 volts. This is not an ideal battery at all. In fact, this is a really bad battery. It should be supplying way more current than it actually is. So there's a lot of resistance inside this battery. I wonder how much resistance is inside this battery. Well, if we do look at our loop rule, I know that there's 6.67 volts here, there's 6.67 volts there, there's some amount of voltage being used by the battery. What is that voltage being used by the battery? It's what the rating is minus the rest of that loop. So what is the voltage being consumed at the battery? It's 5.67 0.33 volts at or by the battery. This is how much voltage the battery is consuming. Well, I know the battery is supplying 2 amps of current. It's consuming 5.53 amps of potential. So let's go ahead and do an Ohm's law. The voltage at the battery should be equal to the current it's supplying times its internal resistance. We can call it Ri. So I got 5.33 volts at the battery. I know it's supplying 2 amps of current. You tell me, what is the internal resistance of that battery? 5.33 over 2. You pop that in your calculator, and I end up with 2.6567. I did it to myself, didn't I? 2.67 ohms. That is the internal resistance of the battery. It tells me how non-ideal, how inefficient my battery is. So, to recap, we've got ideal versus real batteries, and I can find, using Ohm's law and my loop rule, junction rule type stuff, I can go ahead and figure out what the internal resistance of that battery is. If you got any questions, drop in the comments, send me an email, ask me in class. Until next time, see ya.